Um, her first name was actually Amelie, but she always used Emmy. And although this is a picture of her later in life, it's the one that I always uh, associate with her uh, because she looks a lot like my maternal grandmother, who lived in the house next to ours as I was growing up. I have a younger picture of her coming up, but this is the one I think of when they say Emmy Noether. All right, so this is a story of two German universities, or at least largely so. So I thought it would be worthwhile to um, locate them in the country of Germany, Netherlands, and Czech Republic and Austria down here. So Erlangen is in the south near to Nuremberg, and Göttingen is sort of out in the middle of nowhere, not too far from Hanover and Leipzig, but not much is closer. Brunswick, maybe. So those are the two university towns that she lived in and worked in most of her life. So she was born on the 23rd of March in 1882. Her parents were Ida and Max. I should try and pronounce that in the German way, Maxdetta, but I think I'll stick to Max. Was a professor of algebraic geometry and algebraic functions at Erlangen, the southern one. He had several theorems that were attached to his name, but as Wikipedia says, Noether's theorem usually refers to a result derived from the work of his daughter, Emmy Noether. And later, when somebody referred to Emmy as Max's daughter, Edmund Landau, who was a colleague of Max's at Erlangen, said, Max is Emmy's father. Emmy is the center of the coordinates in the Noether family. And girls weren't allowed into the so-called gymnasium, which is essentially the college prep high school. But she qualified in 1900 as, at age 18 then, as a teacher of languages. I think her specialties were French and English, and started to attend the university at Erlangen. She was one of two women in the class out of 1,000 students. Now, women could only audit the classes, but their graduation for them, for German universities at the time, was done by not by college credits, but by did you pass the final exam? So, with her father as a tutor, she could do that, and so she passed the final university exam in July of 1903. Then for a semester, she couldn't go to Erlangen for graduate school, so she went to Göttingen for a year, for a semester, I guess. Yeah, one semester. And there she met Felix Klein and David Hilbert, who were basically the big names in mathematics at the time. Göttingen was the real center of German mathematics at the time. And so she got to meet them, but then they changed the rules at Erlangen and let women into graduate study too. So then she went home and worked there. She finished her first doctorate. The German system, you get two doctorates. The first one is what they call the doctorate. The second one we'll get around to later. It's called a habilitation. And that's eligibility for tenure. But that was in July of 1908. Her thesis was on invariant theory. And then she worked at Erlangen without pay for 7 years, but she could live at home, so she could do that. Now, when people say she did a thesis in invariant theory or something, it would be real nice to be able to say something about what that was. But I can't do any of this mathematics justice. It's a too abstract for our most of what we do, but at least we've seen quadratic forms in linear algebra. So what about this quadratic form, ax squared plus bxy plus cy squared, a form because every term has degree 2. Um, what? How do we say that it doesn't change its value if I switch the x and y's to x prime, which is a linear combination of x and y prime, which is a linear combination of x and y, but we require that the um, determinant of the PQRS be 1. So only certain linear changes of variable can I get away with. Well, if you think about it, that's when the matrix, this matrix and this matrix commute with each other, when TU is equal to UT. So in other words, when that matrix that you get out of the A, B, and C commutes with SL2R, in other words, the special linear group of 2 by 2 real values. So such a form like that is invariant under this group of matrices. Now that's what we see in our linear algebra course. According to Hermann Weyl, her thesis, the one for her doctorate, ends with a table of the complete system of covariant forms for a given ternary quartic. So instead of degree 2, degree 4, and ternary, so 3 variables instead of 2 variables. And it consists of no less than 331 forms in symbolic representation. Even she referred to that as crap in her later years. So anyway, after 7 years at Airline, in the spring of 1915, Noether was invited to return to Göttingen by Hilbert and Klein, and their effort to recruit her, though, was blocked by the philologists and the historians among the philosophical faculty. Women, they insisted, should not become Privatdozenten. A Privatdozent was sort of a private tutor. She gave lectures, but the students paid her, not the university. And one faculty member says, what will our soldiers think? Remember, this is 1915, the middle of the First World War. What will our soldiers think when they return to the university and find that they are required to learn at the feet of a woman? And Hilbert responded, I do not see that the sex of the candidate is an argument against her admission as a Privatdozent. After all, we're a university, not a bathing establishment. Which probably didn't go over well with the philologists and historians and didn't help his case at all. But he said it. Anyway, so why was she invited at all? So I got this bit from a little blurb from the American Journal of Physics. Soon after Einstein introduced general relativity in 1915, Hilbert derived the field equations from a variational principle. And I don't claim to understand any of this at all. This is physics. So Hilbert encountered a puzzle regarding energy conservation, which classical mechanics connected to invariance under time translations. But in general relativity, a global time coordinate does not exist. So Hilbert asked Noether to investigate, and her response applied transformation group theory. Remember, SL2R is a transformation group to general relativity, and created a formalism that went far beyond resolving Hilbert's problem. So according to Wikipedia, the way Wikipedia says it is, Noether's theorem shows that a conservation law is associated with any differentiable symmetry of a physical system. Okay, I don't know what any of that means. But here's an earlier picture of Emmy, and they're trying to tell you something about symmetry. That doesn't look, however, like a continuous symmetry to me. That looks like a discrete symmetry. You just flip the butterfly over and it matches with itself. But I don't, I'll take their word for it. Anyway, if there's a continuous symmetry, then there's a corresponding quantities whose values are conserved, is what she found. Now, how important is this? Well, according to Letterman and Hillen, in a book called Symmetry and the Beautiful Universe, Noether's theorem is certainly one of the most important mathematical theorems ever proved in guiding the development of modern physics, possibly on a par with the Pythagorean theorem, which of course is basic to a whole lot of stuff, even physics. Wigner, though, he was the Nobel 1963 Nobel Prize in Physics, and I read what he says as sort of downplaying it. Her contributions to physics that are most often quoted arose from a suggestion of Felix Klein. Now, I read that as Klein realized that it had something to do with transformation groups, and so Klein called her in to help, and she did the work. But of course, Wigner, like most physicists, says if it doesn't involve an experiment, it's just or a new basic idea, it's just arithmetic, so it's trivial. Now, anyway, at least he says that, in a way that was at the time novel and should have excited physicists more than it did. But most physicists know little about her. All right, so I'll give the last word to Einstein. Yesterday, I received from Ms. Noether a very interesting paper on invariance. I'm impressed that such things can be understood in such a general way. The old guard at Göttingen could take some lessons from Ms. Noether. She seems to know her stuff. All right. So, in her first years teaching at Göttingen, as a pre-med eventually, she didn't have an official position and was not paid. Her family paid for her room and board and supported her academic work. And often her lectures were advertised under Hilbert's name. And then Noether would do the assistant professor duty. She would do the lecturing. But finally, in 1919, the university allowed her to proceed with her habilitation, her second doctorate, which made her eligible for tenure. And finally, in 1922, she became I love the German words, even though I probably will mispronounce them, nicht beamteter außerordentlicher Professor, an untenured professor with limited internal administrative rights and functions. Okay, and she still didn't get a salary. Okay. She wasn't paid until she was appointed to be a Lehrbeauftragte für Algebra. And that was a year later. So that was 1923. She finally got a salary. All right. So then the second epoch of her research, she and Schmeidler. Now, I haven't heard about the physicists in this story, but I have heard of the most of the mathematicians, Klein and Hilbert and so forth, Weil. But Schmeidler, I've never heard of before researching this talk. But the two of them defined ideals in a ring, and the next year she published ideal theory in ring domains is the next one. And there she defined what Kaplansky called Noetherian rings. In other words, every chain of ideals that gets bigger and bigger and bigger stops. Now, those of you who have had linear sorry, abstract algebra, know what ideals are. But those of you who haven't uh, don't know what I'm talking about. But at least in the set of integers, the set of multiples of a given integer is an ideal. So you can get descending chains of ideals that never stop. All the multiples of 4 are already multiples of 2. All the multiples of 8 are multiples of 4. So these are contained that way, and they get smaller and smaller and smaller. But if you get an ascending chain, 400, all the multiples of 500 are multiples of 100. All the multiples of 100 are multiples of 50. All the multiples of 50 are multiples of 10. All the multiples of 10 are multiples of 5. And after that, there's just everything, all the integers. So if you've got the ascending chain condition, in other words, if the ring is Noetherian, then there are a lot of things that are true. And one of them, which I never developed a feel for, but at least I can draw pictures of it. So I thought I'd mention it here. Noetherian rings have what they call primary decomposition. So here's the Noetherian ring, all the polynomials in 2 variables, x and y, with complex coefficients. That's a Noetherian ring, trust me. Right? So if I have an ideal in there, the set of points in the complex plane on which every ideal in I is constantly 0 is an algebraic variety. So what do you mean by that? Well, this algebraic variety here, this set of points in the complex plane, corresponds to, well, part of it is the parabola, y equals x squared. Part of it is the straight line x plus y minus 1 equals 0. And part of it is the point where x is 0 and y is 2. So if you get a polynomial that's in all of these things, all of these ideals, in other words, in their intersection, then it vanishes on that whole set of points. So the bigger the ideal, this is a bigger ideal. It's got 2 generators versus the single generator over here. So the bigger the ideal, the smaller the variety. It's only a point, not a curve or a line. This one has this variety has 3 irreducible components: the parabola, the line, and the point. And every ideal is an intersection of primary ideals. Some of them are as they say, isolated, and all of these 3 are isolated. But this ideal has an embedded primary component, because the set of things that polynomials that vanish on here are just well, the set of just the ones that vanish on the y-axis, where x is equal to 0. But somehow x comma y is a fat point. It's more important. It's an embedded primary component. And so the embedded primary component is not uniquely determined. You got to have the x, but you can have different things that get you the single point, the origin on the y-axis. All right, let's get back to Emmy and out of the mathematics. So she spoke quickly. She talked very fast, and so some pupils, students who disliked her style, often felt alienated, but her most dedicated students loved her enthusiasm, and she developed a group of colleagues and students that she called the Noether boys. Some of them were from China and Japan, who thought along similar lines as she did. those who weren't tended to leave her lectures early because they couldn't keep up. In fact, Emmy Noether, who was actually a colleague with one of the Noether boys, he had a method of talking math with her. He would ask her a question, and she would talk. They would, as they were walking, and as they walked around, she was talking and talking and talking very fast, and he couldn't keep up. Walking, yes, with her, what she was saying, no. And half an hour later, she was, I didn't understand a word. Please tell me again. And she would start again, a little slower. And by the third time around, he finally was able to understand her because she was tired. Third epoch. Wikipedia says in her third epoch, she published works on non-commutative algebras and hypercomplex numbers, and united the representation theory of groups with the theory of modules and ideals. Well, I don't understand that terribly well, but I know one non-commutative algebra is the ring of n by n matrices with real entries, as long as you fix the n. So that gives you at least a little bit to hang your mental hat on. She helped out all over the place. Van der Verden's second volume of Moderne Algebra was her ideas. I saw an English translation of that when I was in graduate school and studied out of it for a while. She worked with Wolfgang Krull on his dimension theory. Pontryagin and Chevotaryov, I've heard of him, but I don't know if I can pronounce it correctly, praised her contributions to Galois theory, and so on and so on. In other words, she was becoming the world's leading algebraist. So Noether's colleagues recognized her 50th birthday in 1932. Hasse dedicated an article to her in the Mathematische Annalen, which is a big name journal. And in November of the same year, Noether delivered a plenary address at the International Congress of Mathematicians in Zurich. And the 1932 Congress is sometimes described as the high point of her career. But the next year, she was Jewish, so the Nazis barred Jews like her from teaching at Göttingen. She realized time to go, so she moved to America, and she took a position at Bryn Mawr. And even though a long time ago she had been an English teacher, she hadn't mastered English well enough or undergraduate teaching well enough, so they couldn't really hire her. She had to get her salary donated by various foundations, but she enjoyed it. And even at Bryn Mawr, liberal arts school, she was able to get Noether girls around her as postdocs and one doctoral student. And she occasionally lectured at the Institute for Advanced Study, but she remarked about Princeton that she wasn't welcome at the men's university, where nothing female is admitted, even though the institute is on Princeton's grounds. But she was only at Bryn Mawr for 2 years, and then she died from complications of an operation for a pelvic tumor. So she's buried on or her urn is under the stone on the Bryn Mawr campus. It's all it's got is her initials and her birth and death dates. And in the New York Times, in an obituary, Einstein wrote, Fräulein Noether was the most significant creative mathematical genius thus far produced since the higher education of women began. Probably Weil was the one who was telling him this because he never met Noether, and he wasn't really a mathematician; he was a physicist. But these are all mathematician, commutative algebraists that I've met, and I thought that we should see some of them. I would point out that Irena Swanson is now the department head at Purdue. She was at Reed College, which is another liberal arts college in Oregon, for years and years until she took over an R1 university, research university. Sylvia Wiegand is still at Nebraska. Susan Lepp is at Williams. Mary Martin used to be at Colgate. She's now at Middle Tennessee State. And the bottom row here are all, a lot of these women are contemporaries of mine. So these three are emerita, they've retired. But just a few of the women in commutative algebra that I'm aware of. I should give you a list of my sources. There were more, but these, I got to be fair that a lot of this came from Wikipedia. And Kimberling's article from the Monthly is also the main biographical part of Brewer and Smith. Jim Brewer was my advisor, doctoral advisor. And there's a Kaplansky that I mentioned earlier. And this is the one from the American Journal of Physics that I thought might be helpful if somebody wants to understand her contributions to physics better. So I hope this is helpful, but I was hurrying to stay within the 20 minutes or so guideline. So you're welcome to look at this. I'll try and make it available if you wish, the slide deck, but I'm afraid that it might be lethally boring, as Dilbert said yesterday. So I'll just say thank you and call a halt.
Thank you, Professor Lantz. That was an excellent presentation. Definitely learned a lot of things. So I'd like to open up now to question and answer. So if anybody has questions, feel free to unmute yourself and ask.
I have a question about the math portion that you mentioned, where you were talking about the varieties. And you said that the origin was a fat point.
Yeah.
Are you able to elaborate on what you mean by that a little bit?
Only that if we say, look at all the functions, what are the functions that vanish, that are equal to 0 for every polynomial that I can write as something times x squared plus something times xy? Well, because x is a factor of that, as soon as x is equal to 0 on the y-axis, those two things will be 0. But that's not enough to describe that ideal. Somehow the things are at the origin are even more 0 than than most of them are, and so the algebraic geometers, who do not include me, describe an embedded variety where the point is inside another part of the variety. They call it a fat point. That help any?
Yes, that does. I see what you mean now. Thank you.
It's like a double multiplicity thing.
Yeah.
So where like the parabola and the line intersect, would those also be fat points then?
The parabola and the line, yeah. Gabe, maybe you can answer that better than I. I don't think they are.
They're not.
Yeah.
So the thing is, like the one that Professor Lantz is saying is a fat point, is because the point itself is a variety.
So it
Right.
has to like strictly be a subset of another
Right,
portion.
right.
Okay.
So it has to be the point and then something else.
Okay.
Yeah.
It's the x squared y part together with the x that makes it 0. Anything else?
For anyone who is interested, this is on chapter 4 of Ideals, Varieties, and Algorithms of Cox-Leroy-Lenoche. There's like 2 sections that explain really well how this works. Unfortunately, you have to read the other 3 really well to understand that. But that's the game. It's a fun game. It's beautiful.
I think I remember something about Emmy Noether having a political point of view that was part of the reason they wanted to keep her out of Göttingen, and maybe also that she left Germany, although obviously being Jewish, she wanted to leave. And I did read somewhere that someone phrased it as maybe one good thing about her dying relatively young, although at the time that wasn't considered all that young, is that she didn't have to see what happened to Jews and others in Europe.
That's certainly the last part is true. She died at 53, which is still strikes me as young, even in that day and age. But yeah, she was sort of a proto-communist, but she didn't bother much with her with politics. She was much more interested in the math. So I don't, especially at the beginning of her career, that early, I don't think that hurt her too much in Göttingen. Might have, and of course it hurt her when the Nazis took power.
Mm-hmm.
But
Also,
she was definitely leftist.
Also, when she was older, she dressed, I believe, all in black, sort of voluminous dresses that made a little kid at her friend's house think she was a priest. And people joked about, they called her Der Noether, which does, Noether sounds like neuter, so then it would be Das Noether. And she also dressed sort of neutrally, I guess.
The Der Noether apparently came from her buddy. I think it was not Pontryagin, but another Russian mathematician, a topologist this time, and she actually visited him in Russia for a while, and they were great buddies. But he kidded her that she was Der Noether, a masculine German pronoun, instead of Die Noether.
Mm-hmm.
I don't know how close it is to neuter or not, whether that gets into it or not.
Well, I read that connection somewhere, but who knows?
Mm-hmm.
One question I had is, you mentioned the Noether boys. I was wondering if she had, like being a female in Germany and having like kind of been discriminated against and had a difficult time finding her path in mathematics. Did she bring other females in Germany into that group, or is it just males?
I'm not aware of, I don't remember seeing any reference to women, as we pointed out, there were, or as was noted in one of these things, she was one of 2 undergraduate students at Göttingen, at Erlangen, when she entered college. And so I don't think there were many graduate students, women graduate students, to bring into her school, in mathematics at least. But the Auguste Dick, who wrote about her, was she's a woman, but she published in '81, so she was definitely not a student. I wasn't aware of Noether boys in Germany.
And Bryn Mawr is a women's school, and it's very small, but it also has a PhD program, and apparently did then if she had a doctoral student in math. So the women's colleges here really promoted women going on. And I know from my daughter having just finished Bryn Mawr, they say Bryn Mawr women don't just marry. So in the old days, you went to college you got an MRS degree, supposedly you were just looking for somebody to marry. And the point is that at Bryn Mawr, they might marry, but that's not all they do. So that's why they're Bryn Mawr girls.
Any other questions? All right. If not, I think this is a good place to wrap up. I want to thank you, Professor Lantz, one more time. This is a great presentation, and we're looking forward to Professor Hart's in 2 weeks.
Very good.